if you remove a file, it removes the inode, and as you read through, you'll see that there is no inode entry for whatever that file was, and even though the file still exists in the layers below, you won't be able to see it. If you modify a file, let's say you're trying to hijack LS, and so you're replacing it with a copy of your own LS. Then you have a new copy of LS inside your read-write layer. You've effectively damaged yourself. But because these layers are immutable, you have not damaged the rest of the operating system, and actually the operating system lives down here. Okay? So this is how you can containerize an application and partition it off from the operating system through the file system. Now there are other things that need to be done because of the proc file system. You need to prevent this application from seeing the other applications that are running on the computer, because that's just a form of information leakage. And so, fortunately, proc is a file system, right? There are extensions inside the Linux kernel in order to basically indicate that you are running a containerized application and it needs to have its own version of proc. Okay? Who's familiar with the proc file system, or do I need to talk a little bit about proc?
I'm vaguely familiar with it, like the high-level idea behind it, but there might be some details we're going into.
Okay, so at some point in time, information inside the Linux kernel was needed to be used by programs. Actually, it's always been needed to be used by programs. But the thing is that sometimes it's not so easy to write tons and tons of tools that tie this information to your running program. You know, you might have to write libraries that talk to the kernel to get the information back out through system calls and so on and so forth. And at one point in time, the designers of the Linux kernel adopted this idea that they thought would be really neat, which is there's the traditional, in a Unix system, everything is a file. Okay? So why not expose the kernel information to the programs that need it as files, using the same permissions that the file system uses in order to partition off whether or not you should be able to read something. So the kernel now mounts a proc file system which provides binding to the kernel itself such that when you read the entries in the proc file system, there are libraries behind it that do system calls into the kernel and present the kernel information outwards to the application. One interesting thing is that you can look underneath the proc file system and you can find your process ID. And if you find your process ID, you can dig around inside there and you can eventually determine underneath your process ID what file descriptors your process has access to. And they're numbered there. You know, and for those of you who are familiar with file descriptors, who's familiar with the standard file descriptors? Standard in, standard out, standard error. 0, 1, and 2, according to the standard that C stood up a long time ago. Well, you can go over there. You can find underneath, you know, your PID number, you know, your file descriptor 0. Okay, standard in. And you can cat information into that file. And it will route it to your program as if you had typed it on the keyboard. Whoa. Because you're catting information into a file. This file is backed by the entry inside the kernel that basically indicates input destined for this program. Likewise, same thing with standard out, you know, although really you don't necessarily have to route through the program to do that, but if the standard out's been redirected, or if you've opened extra file descriptors or closed extra file descriptors, they reflect here. If you're wondering how much RAM your process is taking, which memory pages it's got tied up inside the kernel, all of this information's in here. So you can see that if you could detect the other PIDs of other processes, you're one step closer to breaking out of your jail. The kernel has an option when you launch a program to effectively say, we're going to create a virtual file system for you. It'll have 2 PIDs. Okay? For those of you who remember how programs launch, there's generally an init process. Okay? Now the init process has been mostly taken over by System D now, but it is PID 0. It is the one program that launches all other programs. Okay? So inside the virtual file system, you'll still have PID 0 because just too much stuff doesn't work if you break these fundamental architecture, historic tenets of how Unix is stood up. But the only other process that'll be in there will be you. And so it'll be like you're running all by yourself on a kernel, if you take a look at this. And combining these kinds of kernel table entries along with the layered file system provides you with something called a container. It is a place where you can run a program. That program might not be trusted, but if it's not trusted, it's going to have a heck of a hard time breaking out of its container. And that means that now you can take a PC appliance of some sort, you can run all sorts of programs on it. Programs you don't trust, programs that somebody wrote that you don't even know who it is. And you can have a reasonable amount of security knowing that they won't be able to damage the operating system, and likewise they won't be able to hijack or steal other people's information. And this is wonderful inside a hosting environment. Okay? So this is the foundation of containerization that Kubernetes aims to manage. Who's ever used the old VMware, the one that you install? You can get like 5 or 6 VMs on your computer's laptop before things used to start melting. VirtualBox. Okay, I see more hands on VirtualBox. It's the same idea. You get a little VM engine, you can launch multiple operating systems on it. Okay? What happens when you have 2 computers with VirtualBox on it, and you want those 2 computers to communicate with each other? Not the actual hardware computers, but the VMs inside of those computers. It gets a little bit more complicated, right? You got to wire up one VM to route to the actual network, and the other VM you've got to route to the other network. And then you've got to make sure that, like, for every network address that you've got exposed on one computer, you actually expose 2 IPs, one that will route to the appropriate VM and another one that will route straight through, or you got to do a NATing solution or some other kind of fancy network. All right? And then you got to go over and do it for the source computer too, because otherwise the reply messages won't be able to be responded back to the correct, internal VM instance. And as you add more VMs, you wind up adding more network configuration overhead, not to mention just the regular system overhead of having to log into the VMs and make sure the software is up to date, and so on and so forth. So when we talk about orchestration, the orchestration we're talking about here is literally how do we get multiple computers running a virtualization service of some sort to be running underneath one umbrella that makes it easy to manage it. Okay? And there are orchestration engines for virtual machines. Who remembers OpenStack? Okay. I know you do, because it's probably something that cPanel used to both praise and curse at the same time. OpenStack was an orchestration engine for virtual machines, and it was heavily used by NASA provided the networking code, and Rackspace provided the VM code. Or maybe I got that backwards, but I think that's the way it worked. And it was great for a while. But with virtual machines, you have a lot of overhead between you and the actual CPU. You're running processes inside a virtual machine that is basically itself a process that's also running processes inside an operating system that eventually then touches the hardware. With Containers, your processes exist in the actual operating system that's directly on top of the hardware. So that's why they often say that containers is like lightweight virtualization. It's not true virtualization because you don't have the ability to like emulate a different CPU or something like that. You have to use other technologies, but it's kind of like lightweight virtualization. Point is that Kubernetes orchestrates your containers across a large number of machines. All right, so that is the problem space. Okay? And so now you understand what I'm about to present from the problem space. Do we have any questions before we move on? Yes?
So how many classes would you need to get us, for us to learn this?
Well, I'm going to start with higher level and then just keep going down until basically people stop having interest in it. Because that way, you know, there's only going to be a handful of people who are going to run home and try to implement their own Kubernetes clusters. But everybody, I think, really should have a high level understanding of what this is, how it works a little bit under the covers, and kind of what kinds of problems it's really well suited to solve. So I'm not like going to get into the overly heavy duty nuts and bolts unless people still want it. Okay. Now, if you've got a large number of computers that you're coordinating, the next question is how? Who has ever heard of the Paxos algorithm? Okay, it's basically a way to get distributed instances. If you've got 5 people in the room, and they cannot always be trusted to do the right thing in the next step, and they can't always be trusted to receive a message from somebody or to send a message properly to somebody else, how do you get them to all eventually agree on something? Okay, Paxos algorithm, it's very complicated until you really understand it, and then it's quite simple. The point is you don't need to know the details, you just need to know that there is this algorithm out there that effectively uses a variant of majority rule. So if 3 people understand something out of 5, then reality is what the majority understands. That's how Paxos defines reality. And if one person changes their mind, when it was on the edge of shifting, then you instantly understand the other thing. Because what happens is everybody who's asking has to ask the whole group until they find a majority of like answers. They don't have to get a response from the whole group. That allows machines to shut off and turn on and join and leave the cluster. Okay? But if there's 5 people, you need 3 answers that are all the same. If you get those 3 answers as your first 3 answers, you can stop asking. If you get 1 answer that's sort of an oddball, and then you get 3 answers that are the same, you can stop asking. Only under rare conditions you have to ask everybody. The reason that we cover this is because all of Kubernetes has a backbone. This backbone is a storage system, and the storage system uses a simplified version of Paxos called Raft. Paxos was this wonderful mathematics paper that proved everything and was designed to prove the algorithm. And it was nearly impossible to understand because papers that are written to prove things are not necessarily written in the same way that papers are written to build things. And so eventually Paxos came up with Zookeeper. Has anybody ever heard of Zookeeper? Zookeeper was a distributed knowledge database. It would require majority truth. It it was written in Java, and it was written primarily to handle the big data stuff. So for those of you who remember big data or still use it, it's basically how you process large amounts of data in parallel across large numbers of computers. Zookeeper was really quite complicated. Someone came through, cleaned up the algorithm, and they came up with Raft. Raft is a simplified approach to Paxos, and Raft led us to, I can't remember the name of the cluster now. Huh?
Cluster? Barrel cluster?
No, this is distributed consensus, place. ETCD, the etc. daemon. The reason they call it etc. daemon is because etc. is traditionally in Unix where you store all your config files, because back then they didn't know where else to put it, so you put it into the sort of like other directory. Now it's almost exclusively used for configuration, so now we consider it a configuration directory. So etcd basically does the same thing, but it does it with a spiffier implementation. And this means that if you're building a Zookeeper cluster, one of the first things that you need to do is decide how much redundancy you're going to have in your storage of your configuration information. And you do this by deciding how many nodes you can lose and still have consensus. And this usually means that you build like 5 nodes in. So you can have sustain 2 failures inside your Kubernetes cluster. But from a functional point of view, you can conceptualize the whole thing as just a place to put stuff. If you put it in one node, eventually it distributes out to all the other nodes. As soon as it finally distributes out to 3 of the nodes, then it is deemed existing. Even though, you can say, well, I put it in like 5 seconds ago and it doesn't exist yet. You can actually put it in and query it, and sometimes you don't get the information back, but eventually you'll get the information back as it replicates through. What goes in here? Well, in Kubernetes, the configuration files all have a similar format. Okay, who's familiar with JSON? Who likes it? Okay. Who's familiar with the XML that it replaced? Who likes that? It's wordy. It's easier in some ways and worse in others. JSON fixed the wordiness. And then suddenly we needed some of those words back, because curly braces just are not as descriptive sometimes. Eventually, YAML replaced JSON. So all Kubernetes clusters, by the time that they came out, that was the hip thing to do. They are all configurable through JSON or YAML. And almost everybody exclusively uses YAML, because otherwise you will have objects that don't have names on them. Yes?
Oh, sorry.
Oh, okay. That wasn't it going over your head, was it? Okay, thank goodness. So inside here you have a bunch of YAML files. Okay? So let's say we wanted to add a node to a Kubernetes cluster. So what we would do is we would write a small YAML file. Okay, and it will have a certain format. and it will have a kind in it. We'll say is a node kind. Then it'll have a data section, which will be an object that will contain information about the node that we want to add. And we can do a curl post with this as the payload to the Kubernetes API. And the Kubernetes cluster will now have some entry in here. We'll just call it node 1 in etcd. Okay, is the flow of information so far pretty easy to understand? The API primarily takes requests and stores the objects into etcd. Now that doesn't do anything, right? Because ideally, if we're going to post a new node into the cluster, we want the cluster to try to contact this new node and somehow incorporate it into the cluster. Who is familiar with control theory? Everybody uses it every day in Houston. Well, maybe not now that it's kind of cold, but when it's hot, you've got an air conditioner, right? You've got a thermostat. And your thermostat on your air conditioner, you set it to a temperature. Thank you. You know the answers. Just spit them out. And what happens? When you set that temperature on your thermostat, does your house instantly become that temperature? No. What happens is there is a sensor somewhere that knows what temperature your house really is. And it compares it to the temperature that you set, and then it makes a decision to turn on some systems or turn off some systems to try to get the two to meet. And if it leaves the AC on too long, it'll overshoot. And so there's an entire theory called control theory that's designed about how to provide good control. Kubernetes attempts to leverage this, but instead of leveraging it with things that can be measured in numbers, it tries to measure it with things that Kubernetes calls Kubernetes objects. So every one of the cube servers, which will be located in each one of the nodes, they're like the clients of a Kubernetes system. They report back to Kubernetes, and they write in their own node info. So like if you fire up a client that connects to Kubernetes correctly, that's going to be servicing these containers, it puts its own info into Kubernetes. And so now there's sort of a set of what is wanted and what is existed. And there is a class of programs called controllers. And all they do is compare those two sets. And in the event that these two sets don't match up, they will reach out and do API calls to other things to try to get them in alignment. Remember, the controller does not call one of these kubelets over here in order to set this value. It sets a value inside the kubelet through the API, and then the kubelet has to report back its updated status whenever its status updates, if its status updates. So in this way, it's very much a control loop where the controller has a desired value, it has an actual value, and then it sends control to some system, hoping that when it reads the actual value eventually migrates into match. There are node controllers for nodes. Any object in Kubernetes, which object just basically means a configurable thing, has effectively at least one controller. Okay? And there may be many other controllers that are related to it. But each controller has a particular piece of domain that it controls. So, that's the basic architecture of Kubernetes. And now you've got an idea of how it works. let's talk about some basic security things. All of these APIs flying back and forth have nothing to do with anything you want to do with this system. I mean, have you ever heard, did you hear anything that I described that talked about what you might want to do with the system? No, it's all the background plumbing work that just makes it work, right? Okay. Kubernetes calls this set of communications the control plane. So you've got a control plane, and then traditionally, the non-control plane has always been called the data plane, but I'm not sure if Kubernetes actually calls it that. The idea is that the control plane is the background plumbing, the stuff that makes things work. The data plane would be where your problem lives. So how do I get something into this non-control plane? Well, it's simple. I write an object describing what I want. Not what exists, what I want. I use an HTTP post, and I stick it into etcd, and then I wait for my controllers to catch up and make it that way in the actual system. All right? Which brings me to what is the smallest thing that can be deployed in Kubernetes that resembles a process. Kubernetes actually doesn't manage containers directly, because many times what happens is when you need one container, you might need 2 or 3 containers. The container patterns have now grown to where there are sidecar containers that assist the primary container. There are initialization containers that get the environment ready for the primary container. And sometimes the solution itself just has multiple containers. You might have a logging container in it. And so Kubernetes packages all of these containers into a device called a pod. Now, someone might know what pod means. I don't. I think it's just a reference to things like the traditional peas in a pod, or pods containing, like, if you can remember back when cubicles were called pods, they would contain employees and not necessarily just one. Okay? But the point is that it's a container of containers. So, one of the first things that you would learn to do in Kubernetes is you would learn how to create a pod, and you would submit that pod. And inside that pod, underneath its YAML, you'll see that it has a kind. Kind is the type system in Kubernetes, and the kind will say that it is a pod kind. And then there's a data section in every one of them. And the data section is the details. And underneath that data section, you will find in the YAML, structured and nested, eventually a containers block. And inside the object of that, the array of that containers block, you will have a listing of every one of your primary containers. And there is an init containers block, and there are other things that are in there too, like you can specify how much RAM you want each one to have, and so on and so forth. And when you submit that to Kubernetes, then Kubernetes will do its best to launch those containers on somewhere. And this is the part where things get interesting. If you tied it directly to a node, that node went down, how could the controller ever manage to get that container or that pod launched on that node? It couldn't. This whole system would be relatively useless. Instead, what happens is what's just as interesting as what's specified is what's not specified. What's usually not specified is where these things happen. So it'll be launched in some node inside your cluster. All of these nodes are generally in a flat IP subnet. Even if that flat subnet doesn't exist in the real world, because it will use open VLAN in order to simulate the connections between the nodes with its own network. And this basically means that these pods now are all running in their own little virtual IP LAN, much in the same way that you would have the virtual bridge with VMware, okay? And you can do things like create access points to get in there, you know, and you can create virtual routing rules which effectively act as firewalls, and you can create virtual load balancers that actually understand the other YAMLs that it has in there. So as you add in a new pod, the load balancer will automatically start balancing to that pod because that pod matches the load balancer rules for what gets load balanced to. There are replica sets which effectively rack pods. And so you can say, I need to have somewhere between 3 and 5 of these kinds of pods. And the replica set will make sure that you have somewhere between 3 and 5 of them. There are specialized replica sets that will basically tune based off of load. There are lots of objects in Kubernetes. We're not intending to go through all of them, but we're telling you about Kubernetes in order to make sure that you understand why it has an appeal, why people are talking about it, why people are using it. So who has ever worked on a traditional 3-tier application?
Yeah.
Fantastic. What are the 3 tiers?
Application layer, database layer, oh, what's the third one?
Presentation.
Presentation.
I'm not trying to put you on the spot there. I just wanted to make sure someone was, get a little bit of interactivity. So the thing is that your application tier is usually where we put stuff called business logic, right?
Right.
Over time, they decided putting all the business logic in one process was considered a monolith. So now, we have specialized chunks of the application layer. I don't know. One chunk might have to do with inventory, another chunk might have to do with personnel, third chunk might have to do with cells. Who knows what the chunks have to do with? Okay, it depends upon the problem that you're solving. Imagine for a moment that you have a pre-sales process that checks inventory. Your inventory, because there are so many pre-sales processes, is getting bogged down. If you did your architecture correctly of your problem, you can stand up a second inventory handler. But the problem with standing up a second inventory handler is that your cells will be configured to point to the one that it was already configured to point to. So you'd have to reconfigure this to have sort of inventory handler 1 and inventory handler 2, or you could do something else, which is you could introduce a load balancer. Kubernetes takes the load balancer approach. You will find that the load balancers interact with Kubernetes domain name system. So every time you fire up a new load balancer, you get a new hosting. So you configure cells to go to the inventory hosting, and then inventory interacts with your replica set, and it finds every one of the instances that's underneath that replica set, and it makes sure that it balances across all of them. And if one of your instances dies for one reason or another, programming bug, I know, it never happens. someone turned off the node. Then what will happen is the replica set will notice in that, that observed portion of the world, I can't even, that entry has expired. Hasn't been updated since its timeout interval. And it will basically say, oh, okay, I went from 3 replicas to 2, and now I need to bring it back up because this is the minimum of 2. And the load balancer has a load balancer controller, and it will notice the same thing, and it will stop routing messages to the dead replica. And as your replica set controller brings up that third one over here, then your load balancer controller will notice, oh, I suddenly have a matching instance out there that I'm not routing to, and it will rewrite its rules. This concept of borrowing from control theory means that you don't have to have your logic and your control plane communicating with each other in the way that we traditionally did it in the past, which caused all sorts of scalability issues. Likewise, this sells item, this sells bit of business logic, it'll never know. Stuff will just get routed to where it's supposed to be routed.
I got a question.
Sure.
These things you're load balancing, are those containers or are those pods? Or are they both?
So they are pods because pod is the smallest thing that Kubernetes can deploy.
Right.
But the pods may have only one container within them.
Okay.
So the minimum number of containers per pod is always 1.
Okay.
But if you had 3 or 4 things, like sometimes you need unified logging. Okay? Remember, we don't even know which machines these are on. So try to debug it by reading the log files. Good luck. You gotta find the log files first, and like the cluster that I was working on this morning has 20,000 nodes. Not to mention it scrubs the log files like every hour simply because it doesn't have enough disk space. So sometimes you'll put 2 containers in here. Okay, well I shouldn't do it inside a load balancer because that's a component that Kubernetes typically provides. Let's say I do it inside my inventory object. And so one of the containers connects out to our database, okay, slow step.
Right.
And then the other one sends it off to another container, which acts as a log aggregator. All right? So 2 containers inside one process, it can make a lot of sense.
Okay.
All right? Why would you do it as 2 containers inside one pod? Well, probably because it's just simpler to write it that way than to try to write non-blocking, semaphore locking, correct handoff between 2 threads inside one program.
So you're saying by having the containers, you don't have to worry about a lot of the inter-process communication, that sort of thing?
You basically handle all your inter-process communication through the network.
Okay.
It is possible to do more exotic things, but unless there is a high amount of value, you really wouldn't want to do it. Remember, each one of these containers is running in its own file system from its point of view. So if it tried to create a pipe, that pipe would not be shared by another container.
No, the pipe would be between the...
I can't put a pipe between these 2.
Not between the 2 pods, but you could do it between the 2 containers within the same pod, right?
If both of those containers are configured to map to the same read-write layer on my layered file system.
Oh, okay.
If they are configured to map to different read-write layers on the layered file system, then no, they couldn't. Because you would create a pipe in one side there would be no way to put that file descriptor in the other read-write layer.
Okay,
Okay,
very cool.
so that's Kubernetes in a nutshell.
Now let's create and deploy one. Or is that next week? I'm kidding.
My record time for standing up Kubernetes bot from scratch is 5 days.
Oh,
Yes.
So is this, and I've very little experience in this, but it seems the way you're describing it on there from a hardware standpoint, it seems analogous to a RAID controller, maybe?
In the sense that it takes care of some things for you without you thinking a lot about it, yes. In the sense that a RAID controller is usually a piece of hardware that's connected to a whole bunch of hard drives that presents them as one hard drive, no, because everything here lives in a virtual space that's scattered across an unknown number of actual pieces of hardware. You can add nodes to this while it's running. You can remove nodes from it. If you decide that you want to shut down a node, you can put in a posting to say, I want to change the node's labels and say this node is no longer executable. And then you can wait for the processes to exit, or you can evict them if you know that the processes have replica sets or application sets around them. Which, by the way, I didn't talk about application sets. Replica sets are kind of an old way of doing things just so you can get replicas. But there's actually another thing out there called an application set. And all an application set does is it combines 2 replica sets. It has the replica set of what is running right now, and as you release a new version, it makes a replica set of the new version. And it will tune up the size of the replica set of the new version while it tunes down the replica set size of the old version. And that way you can get a seamless upgrade across your cluster, where there is actually a period of time where you're running both versions of the application at the same time. You can even set it to where you stay running, like we'll route 10% of our requests through the new version to see, whether it breaks. And then, like, if we're happy with that, then we'll ramp it up all the way. And if something goes wrong, the application sets have the ability to roll back. And there are tons of Kubernetes objects. There are file objects where you can mount file systems that are remote or local. This is a good way of providing a hole into your actual operating system if there is a resource in your actual operating system that you need, or if you wanted to provide, say, Unix domain sockets, which Unix domain sockets have a number of very interesting characteristics, but one of the main things that they have is they usually have some sort of a server, some sort of a socket, and some number of clients. And this socket has to live in a file system. Well, if these are in different pods, then the only way to do this is you have to put that socket into the operating system, the real operating system, underneath everything. Which means that if the server goes away, granted, if the server goes away, the operating system will close the socket file descriptor and the socket will go away. But theoretically, if the server were to write an extra file right next to it, and then the server goes away, that file's still there. Because you wrote it into the operating system, you didn't write it into the layered file system. And if some people use Ceph, some people use other kinds of backend storage. You've got objects that can provide you access to Ceph volumes. Jared, you've used databases. You probably had a point in time where you wondered How in the world am I going to store the database username and password in some sort of a secure way? Okay, there's lots of systems that do this. One of the most popular is HashiCorp's Vault. Basically, you can correctly authenticate yourself to HashiCorp's Vault. HashiCorp's Vault will give you back some information. That information should be controlled and not displayed to the screen and all sorts of things. Kubernetes has an entire category of secret objects. There's an external secret, which you can basically say, I expect when I launch to use this external secret, and then there is a secrets controller that will then take the information that you have about your launch and use that information to route it over to a secrets provider and see whether or not it can create a secrets object. In doing this, you can have application developers absolutely not even know what their database username or password is, ever. There's lots and lots of really cool, nifty tricks in Kubernetes. At the same time, you wind up rewriting your programs to leverage them. And that means that your programs start to follow a certain kind of pattern of implementation. It's very tied to microservices. All right. I think that's about as deep as I can go on the next path of detail.
Pretty cool.
I don't want to burn you guys out, but I want to know, is there interest in going deeper either at another time or for the remainder of this evening?
I don't know about like the remainder of this evening, but I think it'd be interesting to see you maybe create like a basic container and a pod. And I don't know. You have the tools to do it like a basic.
I could
thing.
do that. Let me see if I can fire up an EKS cluster so I don't have to build my own cluster, because remember that record time thing. And see if I can do that. There is a command line tool that does most of the submission of the YAML files for you called kubectl. Okay, and kubectl has all sorts of support for things like multiple configurations to point you to different clusters. They call them contexts. So you can, use one computer to manage multiple clusters. There's a ton on it. I mean, literally, if you wanted to get a CKA, which is sort of, it's supposed to be a certificate, which, you know that certificates are the things you're supposed to get to prove that you actually know something after you've learned it, right? But a lot of people wind up using the CKA in order to prove that instead of they've developed some degree of skill in there, they just at least understand basic concepts. I don't have an opinion on which way you go about it, but to tell you the truth, if you wanted to learn the basics, then I would say that overall it would probably be around 36 hours of honest work. Okay. And that's you take a break every 20 minutes for 5 minutes, that's not included in the 36. You have to sit there and muse on something in order for it to gel. That's not included in it. I'm saying 36 hours of truly honest work. The way that the cluster starts up initially is also pretty interesting. Docker and all of the container-based infrastructure has a support for launching containers on PowerUp. And so you can put in your configurations, there's the client for the node that will accept the requests to launch pods is called a kubelet. And you generally install the kubelets in such a way that as your Docker engine initializes, or whether that's Podman or something else, it will then read those configs and launch those pods. And that's how your cluster forms itself at the beginning. Because obviously, if you have no nodes, you can't add a node. So it's gotta be bootstrapped somewhere. And then there are various other services too.
So just to recap, a container has one or more processes that you need.
No, a container is usually tied to just one process.
Just one process, okay.
Yeah, it's the pod that has one or more containers.
Gotcha.
Well, thank you very much. Floor is open for more questions.
Very good.
Who thinks they will be using Kubernetes soon?
Everything's going to the cloud. I wouldn't put it past the company I work for to ask me to do something with it.
Amazon has something called ECS, Amazon Compute Services. It's sort of like a pre-Kubernetes version of effectively container orchestration. EKS is the Amazon Kubernetes. By the way, if you're Googling this, Kubernetes starts with a K, K-U-B-E-R, okay? It's Greek for houndsman. There's tons of ship analogies. For a good example is Harbor is the image service where you would pull your Docker images from. And you know, it just keeps going from there. But the point is that the Cloud Native Foundation, CNF, I think, they basically are the people that are pushing Kubernetes really hard, and almost everybody offers some form of it. Even HPE has its own branded version of a Kubernetes engine called Emerald Compute Platform, ECP. Alrighty. Thank you very much.
Very cool.
I'll see if I can put together something. I'm not sure it'll be ready by next week.
Yeah, just like, so what would be like an example of just like a simple cluster, like generally, like you have one process that does what, like accept a web request or something for
Yeah,
hello world
so
or something like
some of
that?
the simplest examples are just web servers.
So you have one container that has a web server, and
Right.
then you put that container in a pod, and then theoretically, if you deploy 300 of these, you just deploy 300 web servers?
Yeah, that would all be serving exactly the same information.
Interesting. Okay.
And if you put a load balancer in front of it, then, you know, they'd all be receiving one